Hi, welcome to the first video in a series about the Leibniz binary subsystem, an interesting family of modules created by the Polish maker Xaoc Devices. This video will be all about DREZNO, the core module of the system. DREZNO is an 8-bit binary conversion computer with an analog to digital converter and a digital to analog converter. The same kind of converters your sound card or audio interface are built around. DREZNO has a bit depth of 8 bits and an internal sample rate or clock of 2 MHz. For reference, a standard audio CD stores information in 16-bit at a sample rate of 44.1 kHz, which is 8 bits more but almost 50 times slower than the internal clock of DREZNO. DREZNO gives us the ability to manipulate the signals that are going through in a variety of ways. For example, you can remove single or several bits by simply not patching them. You can replace bits by sending in gates, CV or even LFOs and VCOs. You can also play around with the sample rate by sending in your own clock into the ADC or DAC, further expanding the sonic possibilities of this elusive piece of gear. You might be wondering how the bits in DREZNO represent anything related to audio or voltages, but with some imagination you could look at DREZNO as a kind of sample module that works with an extremely fast clock but is limited to 265 quantized values. Every voltage that we send into the ADC converter is sampled and represented by an 8-bit binary number that we call a byte. We can access every bit in this byte as a signal that's either on or off, so in essence these are just gates. Every byte, which is a binary number composed of these 8 bits, represents a certain output voltage that we can extract from the digital to analog converter output, which is just the main output. When we send in an oscillator or any kind of changing voltage, these binary numbers are constantly changing as the input voltage is being sampled every time the analog to digital converter receives a clock signal. At 2 MHz and 8-bit, there's not much of a change when we simply patch a signal into DREZNO and back out. It's by manipulating the values of the internal sampler that we can achieve interesting results. Later on I'll show you a diagram in which I go over this again, and we'll have a look at a sine wave going through DREZNO to see what manipulating these bits looks and sounds like in real life. And while it's easy to predict what's going to happen when we're processing a simple wave, it's nearly impossible to know what's going to happen once you run a more complex signal through it. But in my opinion, knowing what's going to happen is not the point of DREZNO. I think it's more realistic to approach DREZNO like an interesting kind of wave folder that you can feed anything you want. No way that anyone exactly knows how many volts a sound will get when you apply a certain voltage to the modulation inputs of a wave folder. For the most part, it's more about trying out different settings until you find something useful or interesting, and this is really how I tend to work with DREZNO. I want to express my gratitude towards the people at Xaoc Devices for sending me these units so I can learn them and try to make a few comprehensive videos about them. Let's first listen to some patches I made before taking a look at what we can do when we run a few simple signals through DREZNO. Let's have a quick look at a schematic representation I made to make sense of what's happening when we send a signal into DREZNO. So to the left we have our analog sine wave oscillator. Let's assume that the clock rate is really slow, we see it here at the top. Every time the analog to digital converter in DREZNO receives a clock signal, the voltage at the input is sampled and converted into a binary number of 8 bits long. We can see these numbers here to the right. When we now look at the front panel of DREZNO, we can see that the binary number, for example the top one, is represented by the yellow LEDs. When we link the input to the output with the link button, the signal coming from the output would be something like this. And I think you can see that a faster clock rate would result in a better representation of the sign we sent in, but sometimes this is exactly what we want, and that's why there's a clock input, so we can patch any clock signal we want to use to clock the conversion. The jacks on the left of the unit are the analog to digital converter bit outputs, And these outputs send out gates according to the status of the bits. It doesn't matter if the input and output is linked or not. We can use these gates for anything we want, but of course you can send these into the digital to analog converter bit inputs to the right, which would result in an analog output that's even more altered than it already was. In this section, I will run a simple sine wave through DREZNO, and I'll show you different ways to manipulate the sine wave or any wave you send into DREZNO really. I will also show you what these sliders are for, what the link knob does, and how you can set up DREZNO as a sequencer for pitch or triggers. Let me remove all this and we'll start from scratch. Here we are. The top trace on zero scope is a sine wave coming from January 3. I've routed this sine wave through zero scope and it's going into the analog to digital converter input on DREZNO. The digital to analog converter output, or just the main output of DREZNO, is going into the zero scope as well. It should be the bottom trace, but currently we're not seeing anything. And this is simply because the button at the center of DREZNO, which is labeled link, is not activated. In this mode of operation, the two parts of DREZNO, meaning the input stage, which is the ADC, and the output stage, which is the DAC, are not connected to each other in any way. Let's press this button. And now you can see that the input stage is linked to the output stage, so we're hearing the sine wave that's going through DREZNO. Please keep in mind that although the sine looks exactly the same, the bottom trace is really the analog conversion of the binary information extracted by the analog to digital converter stage. To show you this, I'll just patch up a dummy cable into one of the bits. And you can see how this already changes the output wave a lot. And when the input and output stages are linked, this is exactly the way to manipulate the wave. So by just patching a dummy cable into one of the bit inputs, the output stage of DREZNO, it's missing all the information about bit 6. Instead, it's just receiving 0 volt. And what this essentially means is that the binary information extracted by the ADC input is changed, and when this changed binary information is reconstructed by the DAC output into an analog signal, this is what comes out. Now what you can also do is, instead of just patching in a dummy cable with no information going in, you can patch any of these bit outputs, which send out the singular bits as gates, and we can connect any of these to any of the bit inputs, which also changes the sound but in a different way. And rest assured, I have no idea what's going to happen when I connect bit 4 to bit 6 or when I patch in a dummy cable. An easy way to look at this, and I will show you in a moment, is that the most significant bits, meaning the bits on the top, are changing the slowest, but cause the biggest change in the sound or in any voltage you send in. And the lower bits here, the least significant bits, are changing the quickest, but inflict the smallest amount of change in the sound or voltage. Let me show you by patching the first bit into the last one. You can see that the wave changes drastically and it's moving really quickly. Now as I go up, you can see how these little oscillations in the wave are getting bigger but slower. And now by patching the bit output of bit 7 into the bit input of bit 7, we're back where we started, just as if nothing was patched. Alternatively, if you patch the most significant bit output into the least significant bit output, you won't see much of a change, because even though it's changing really slowly, when we're not feeding this slow changing information into one of the most significant bits, we won't see much of a difference. But when we go up, you will see how there's something changing in the output wave. And now if you start combining different bits with each other, you'll see how we can drastically change the shape of the wave even more. Let's patch 6 into 7, 7 into 5. And you can see by making different combinations, you can get all kinds of waves. It's really interesting just to experiment with this. Now keep in mind that for every input that we didn't connect on the output stage, it's just using the information extracted by the input stage. So in essence, these bits are trying to keep the shape of the sine going, and the ones I patched into the bit inputs change the sound. Now when I disengage the link, the bits I haven't patched up in the output stage are just not represented in the output. So if I start removing cables, you'll see how eventually we just end up with a really basic kind of square wave. And again, you can see when we're in the unlinked mode and we don't patch anything up, nothing's happening. Now of course we can just go ahead and connect bit 7 to bit 7. Let's connect 5 to 5. Let's connect 3 to 3. You can see how we get kind of a rudimentary sine-like shape going. But when we start changing out bits, it starts getting interesting again. And this is all from a simple sine wave. And this is what happens when I attenuate that sine wave. Let's change the tuning of this oscillator. Now this is the slowest my Generate 3 in audio mode will do, so I'll switch over to low or LFO mode. Even though my scope isn't having it, there really is some kind of LFO getting through, as you can hear. Please keep in mind that we're currently listening to an LFO. In this mode you can clearly see how the LEDs are changing, thus the gate outputs of the input stage are rapidly changing. Patching these into different bit inputs on the output stage results in audio rate oscillations, even though I slow the sine down really low. And we are still getting some kind of audible signal from the output of DREZNO. Now let's remove all this. So now I will show you how you can use DREZNO as an interesting LFO. I'm still using Generate 3 as an LFO. It's going through the scope. It's the top trace into the ADC input on DREZNO. The output, which is currently linked to the input, is going through the scope. It's still the bottom trace. And this is going into the modulation input on a filter that's in bandpass mode. Let me turn down the modulation on the filter a little bit. Let me slow down the LFO. And now you can see that the bottom bits, being the least significant ones, are indeed the ones that change the fastest, but they will inflict the least change in the output of the wave. And the top bits, being the most significant ones, are changing really slowly. And by the way, these LEDs represent the binary numbers in the input stage. You'll see, for example, 4-bit 4, which is this one. When I patch this one with a dummy cable, there's nothing changing here, there's nothing happening. Let's patch the first bit, bit 0. The LED here keeps flashing away because it's monitoring the input stage. So now for some LFO mangling, let's try bit 5 and let's route that to bit 7 in the input stage. And already you can see that the LFO we're getting out of DREZNO is really a completely different wave. Let's go ahead and switch out some more bits. I can remove a bit here. So this is just a dummy cable. Let's try this into bit 4. Let's instead patch it to bit 7. Let's patch the output of bit 3, which we're seeing here. By the way, the counting or the numbers on DREZNO start at 0. So bit 3 is actually the 4th LED. It's also the 4th jack here. Let me add a little bit of reverb to this. Now if I unlink the input and the output stage, only the bits I've patched up are used to construct the analog voltage at the output of DREZNO. So let's change some of this. Let's patch bit 2 into bit 7. And you can clearly see and hear how bit 2, being the third LED, affects the output voltage. Now if I patch bit 6, which is the second LED from the top here, to, let's say, bit 5, the output wave is changed even more. And by doing this, you can create really interesting modulations. Okay, let's remove this, try something else. So now I've patched up a pitch sequence coming from Moskwa 2 to my VCO, and I still have the same LFO running through DREZNO and into the modulation input of the filter. Now let's see what happens when I start sending in a clock into DREZNO. Because right now, the input, being the sine wave and the top trace on the scope, is being sampled by DREZNO at 2 MHz. Let's look on the scope and listen. And as you might probably see, the output of DREZNO is a little bit more stepped now. Now let me slow down this clock even more. And this is a really neat and interesting way to get a stepped LFO. And by using DREZNO this way, it kind of acts like a sample and hold. I think it's really interesting. Now, if you start patching up bits and changing them out, let me increase the clock rate again. And all this modulation is just extracted from a sine wave. And it's not truly random either. It's kind of controlled chaos. Now let's unlink the input and the output stage. Let's patch up a bit more. Now you can of course increase the clock rate to whatever you want. Earlier I told you that these LED represent the gates of the input stage, but keep in mind that these are outputs, so you can use these to trigger envelopes or drum sounds or whatever you want. Let me quickly patch up some kind of sound. Let's use orbit in audio mode to create kind of a burst of noise. Let's go through delta V, use it as a VCA. Let's patch the output into the mixer. Let me make sure the levels are okay. Let me change the rhythm by patching bit 1, which is the second LED here. You can get synchronized triggers and modulation from DREZNO. Of course, you can go a lot further by patching up different gate outputs. So you can just keep your eyes on the LEDs. The second bit, or the second LED I should say, is triggering one sound. And the fourth LED, being bit 3, triggers the other sound. Let me patch up one bit more into an envelope, and I'll use this to open up the filter as well. Now we can of course still go ahead and change the clock rate at which DREZNO is sampling all of this. Now let's have a look what happens when we remove the clock. Now this is of course complete mayhem, because these bits start changing at 2 megahertz. But let's patch let me mute those sounds. And by patching a clock into the DAC input stage, the speed at which the input is sampled and outputted from the gates of the input stage is not changed. It's still at 2 megahertz. But we're clocking the rate at which the conversion of this digital information into analog by sending in our own clock. So these LEDs and these gates will fire at a really high rate. Let's mute this. Now let's increase the LFO, which is not linked to the tempo, by the way. Let's switch up some things again. Let's try using a different gate to trigger the noisy percussion sound. Let's increase the clock rate. Let's now patch a random gate into one of the bit inputs. And I think you will agree that it's really interesting to be able to extract a really interesting modulation and a lot of triggers just from one module by feeding it just one clock and a simple LFO that's not even synced to the tempo. I mean, I can turn up the rate, you can still see it on top of Zeroscope here. But DREZNO really doesn't care. Whenever you send in a clock of your own, it stays in tempo. And just by changing the clock rate which I'm sending into the ADC stage of DREZNO, the feel of the patch changes completely. Now to show you what these sliders are used for, I patched up somewhere in this mess channel 3 of mats into the top trace of the scope. From there it's going into the ADC input on DREZNO, and the DAC output is going back through the scope. It's the bottom trace, and this is for the moment not going anywhere. Now channel 3 of mats, when you don't send anything into the input, creates a DC offset of plus or minus 5 volts. Now you will see when I turn the knob to the right, there's plus 5 volts of offset going into DREZNO, and what's coming out of DREZNO is exactly or almost exactly the same. You'll also notice when I turn it down, the minus 5 volts of DC offset, the signal coming out of DREZNO is almost exactly the same as well. Now this took a lot of fiddling around with the knobs, because these controls are really delicate. It's not like you can break something if you don't do it right. That's not a problem. But if you really want the input and the output signals to exactly match, it just takes some time. Now when I turn down all the offsets on DREZNO, and now you can see that the output is gain stage completely different than what I'm sending into DREZNO. So now let me turn mats to 0 and see what the offset here does at the input stage. And let's see what the offset at the output stage is doing. There's a bipolar VCO that's 10 volt point to point, which means in this case it's plus 5 and minus 5 volts. The signal we're getting out of DREZNO right now is something else. Let me again change the settings so you can see. So we're actually clipping, but kind of in reverse. We're not getting the full readout of what's going into DREZNO. And as you probably can also see, the output is almost completely below 0. Now to solve this, you might think turning up the offset is a good idea. But as you can see now, the wave is clipping on the top as well. What you need to do is fine-tune the gain and the offset sliders to get the input and the output signal to be almost the same. Turning down the gain in the output just attenuates the signal of the output, and turning up the offset actually in this case offsets the wave completely above 0 but also clips it. And what I want you to take away from all this sliding around is that it's really finicky if you want to get the output and the input to match exactly, but there's a lot of possibilities to actually tune the output exactly like you want. And this is where I want to show you how you can use DREZNO kind of as a sequencer. Now first let me patch up a slow sine wave to the input of DREZNO. And as you can see now, there's a sine wave coming from Pamela, which is a digital LFO, so it's completely positive. It's going into the scope and into DREZNO, and the signal we're getting out of it is almost exactly the same. Now let's use output of DREZNO to actually control the pitch of my VCOs here. I'm using two generates, they're both receiving pitch information, and one of them is just phase modulating the other one. And by using DREZNO in unlinked mode and only patching up 2 bits, we're restricting the possible output values to 4 values in total. You can just calculate this by doing 2 to the power of however many cables you connected. So that's 4 possible output values. If you connect one more, That's 2 to the power of 3, so there should be 8 different values coming out of DREZNO. Now to use this as a pitch sequencer, as you can hear, that's complete nonsense, but this is where these sliders come in. You can tune these until you find something that sounds musical to your ears, or amusical if you're into that kind of thing. Now I'm using an output of Pamela's new workout to trigger my VCA, which is the envelope of my filter, but you could just as well use one of the bit outputs as a trigger. So this already sounds a lot more interesting to me than what we started with. But of course we can now clock either the ADC or the DAC to get the pitch changes more in time. And as you can hear, it might take some time to get it set up just like you want, but I think it's worth the effort, because you can get really unpredictable and interesting pitch sequences. Now I can go ahead, change up the rate of my LFO. I can change the tuning by changing the offset. And I can change the range by increasing the gain of the output stage. Of course, this also influences the scaling, as the output is completely not quantized to any 1 volt per octave scale. But nevertheless, you can get it to act like it is. This is just achieved by playing around with the sliders on DREZNO. And of course you can go ahead, patch up a random gate to the input stage as well. There's really no limit to what you can do with this. Now I can use another one of these gate outputs to trigger the envelope that's going to my filter. Earlier I had it linked to the trigger that was opening the VCA. Let me try using the first bit, which is really going a lot faster. This will be it for this first video in the Leibniz binary subsystem series. I haven't found that many interesting or in-depth videos about DREZNO or any of the other modules in the Leibniz binary subsystem. There's a few though that are really interesting. I will link those in the description so you can watch those. There's also a really interesting talk the people of Xaoc Devices did at the Schneidersladen in Germany. There's a lot of interesting information about the inner workings of DREZNO There's information about how the quantization is happening. And by that I don't mean pitch quantization, but quantization to create digital bits out of analog signals. There's also some really interesting information in that talk about why the clock of DREZNO has to be really precise. It has something to do with quantization distortion, and that is something that happens when you go from the digital back to the analog. I'll also leave that link in the description. Next up, we'll be taking a look at Lipsk to the right here, might be out of focus, and after that I will take a look at Jena, which I think will be the biggest challenge, because this one really takes it up a notch. Take a look at the first video I did in this series. It's actually kind of a prequel video, and in that video I explain how binary numbers work. Not in a lot of detail, but there's just enough information for you to understand how to read binary numbers and what most significant or least significant bits mean. Those are terms I used quite a lot in this video. I hope you learned something by watching this video. If you liked it, please share it with someone. That would be awesome. Anyway, thanks for watching. Bye.